Strip away the interface and the hype, and a large language model is simply a statistical engine. It is a neural network trained to execute one highly specific mathematical task: predict the next token in a sequence. But an out-of-the-box model operates entirely in a vacuum. It relies solely on historical training data, which means it hallucinates when faced with current events, it holds none of your proprietary company information, and it has zero native ability to interact with external APIs. To construct systems that actually function in the real world, engineers divide the AI architecture into two distinct domains. You have the base engine, the internal mathematics calculating probabilities, and you have the application layer, the external software wrappers that connect those probabilities to external systems. Scaling AI in production is less about altering the engine's internal weights and more about managing the data layers that bridge that engine to the outside world. Let's start inside the engine with tokenization. Machine learning models do not read human words separated by spaces. They break text into discrete computational chunks. By splitting off grammatical suffixes like ing or ers, the system isolates the actions being described. But breaking text into chunks is only the parsing stage. How does a machine derive actual semantic meaning from these fragments? The engine translates those tokens into vectors. Every piece of vocabulary is mapped as a coordinate within a massive n-dimensional space. Through the process of vectorization, tokens that share similar meanings cluster tightly together, while opposites are pushed far apart. The base model does not inherently know language the way humans do. It navigates a geometric map where meaning is dictated entirely by spatial proximity. This spatial logic introduces a challenge: ambiguous terms. The word apple shares the exact same spelling whether referring to a fruit or a technology corporation. The transformer architecture resolves this using an attention mechanism. By analyzing nearby context words in the input, like revenue or headquarters, the algorithm mathematically pushes the ambiguous vector away from the irrelevant cluster and anchors it to the correct semantic group. It places the term inside a cluster defined by specific technological peers. The coordinates align alongside other major enterprise software companies. So when financial context is present, the final vector coordinate lands precisely on the tech giant. These vast semantic maps are constructed through self-supervised learning. The model feeds on raw data scraped from the internet, masking sections of a sequence and continuously guessing the missing piece, refining its own internal weights with every attempt. Ultimately, transformers and attention blocks are dynamic mathematical operations. They adjust vector coordinates on the fly to predict the most statistically probable next step based on surrounding context. That covers the internal mathematics. Now we cross over to the application layer. Hard-coding static prompts is obsolete. Today, developers use context engineering to dynamically feed the engine the exact data it needs at runtime. The primary method for this is Retrieval-Augmented Generation, or RAG. When a user submits a query, the application server intercepts that request before the language model ever sees it. The server routes the query into a vector database. Using similarity search algorithms, the database instantly locates internal company policies or documents that geometrically align with the user's request. The system retrieves those specific files, appends them to the original query, and injects that combined package straight into the model's context window. By bridging the gap between a model's static training dataset and a live proprietary database, RAG directly targets and mitigates the hallucination problem. Reading internal documents is useful, but software must also interact with external systems. To standardize this, the industry introduced the Model Context Protocol, or MCP. An MCP client functions as a wrapper. It allows the model to pause text generation, reach out to an external server, and pull live actionable data, like current scheduling for an Indigo flight. Simultaneously, the client can hit a competing API, instantly pulling Air India flight details for a real-time comparison. This protocol forms the backbone of agents. An agent is a long-running software process that leverages MCP and RAG to evaluate options, make logical decisions, and autonomously execute external API calls. Integrating MCP enables the LLM to function as a software component, capable of triggering real-world actions through standardized API requests. In production, computing power dictates architecture. Deploying a 300 billion parameter model for a narrow, company-specific task is often too slow and financially impractical. To solve this, engineers use distillation. A massive teacher model analyzes data and generates ideal outputs. A specialized small language model, or SLM, built with a fraction of the parameters, is then trained to mimic those exact outputs. A global foundation model is necessary if you are an agency running massive weather simulations, but an enterprise sales bot often only requires a distilled expert trained strictly on customer interactions. Once the model is sized correctly, developers apply quantization. They compress the neural network's weights, converting them from heavy 32-bit floating point numbers down to 8-bit integers, reducing the memory footprint during inference. Deploying AI at scale is an ongoing engineering trade-off, balancing parameter size and memory compression against the speed of inference. Even with a perfectly sized engine, the raw mathematical output still needs to be shaped. Fine-tuning runs the base model through thousands of highly curated question and answer pairs to lock in a specific persona and formatting standard. If a user queries the model for historical facts, like identifying a specific US president, fine-tuning ensures the system returns a direct, factual answer, rather than generating deflections like, "I'd like to know that too." To further refine accuracy, developers use reinforcement learning from human feedback. Human graders review the model's responses, assigning a +1 or -1 score to optimize the specific geometric paths the vectors take during generation. Finally, through chain-of-thought prompting, the model is trained to expose its reasoning. It systematically breaks complex problems down into sequential, logical steps before finalizing its answer. Self-supervised learning builds the engine's raw predictive power, but it is RLHF and chain of thought that provide the alignment necessary for production safety. Let's trace the complete architecture. A user prompt hits the system and enters the application layer. During context aggregation, the prompt is intercepted. It pings the vector database via RAG to retrieve internal documents, while the MCP client simultaneously fetches live external API data. The enriched prompt then crosses into the base engine. Here, the core computation executes. The data is tokenized, vectorized, and driven through the transformer's attention blocks in a highly optimized quantized state, generating the precise solution. By decoupling the mechanistic engine from the application layer, engineers can cut through the hype and build reliable, scalable AI systems.